Hello, and welcome back to the course on deep learning. Now that we've seen neural networks in action, it's time for us to find out how they learn. So let's dive straight into it. There are two fundamentally different approaches to getting a program to do what you want it to do. One is hard coded coding, where you actually tell the program specific rules and what outcomes you want, and you just guide it throughout the whole way. And you account for all the possible options that the program has to deal with. On the other hand, you have neural networks where you create a facility for the program to be able to understand what it is doing on its own. So you basically create this neural network where you provide it inputs, you tell it which one has outputs, and then you let it figure everything out on its own. Two fundamentally different approaches, and that is something to keep in mind as we go through these tutorials. Our goal is to create this network which then learns on its own. We're going to avoid trying to put in the rules. A good example that I can give you right now is this will come further in the course, but it's just a very visual example. For instance, how do you distinguish between a dog and a cat? For on the left side, on the project that's depicted on the left, you would program things in like the cat's ears have to be like this. Look out for whiskers. Look out for this type of nose. Look out for this type of shape of face. Look out for these colors. You describe all these things and you'd have conditions, like if the ears are pointy, then cat. If the ears are slopping down, then possibly dog, and so on. On the other hand, for a neural network, you just code the neural network. So you'd code the architecture, and then you point the neural network at a folder of all these cats and dogs with images of cats and dogs, which are already categorized, and you tell it, okay, I've got some images of cats and dogs. Go and learn what a cat is. Go and learn what a dog is. And the neural network will, on its own, understand everything it needs to understand. And then further down, once it's trained up, when you give it a new image of a cat or dog, it'll be able to understand what it was. So there they are. Those are the two fundamentally different approaches. And today, we're going to slowly start getting into how that second approach works. All right, so let's get straight to it. Here we have a very basic neural network with one layer. This is called a single layer feed forward neural network, and it is also called a perceptron. Now, before we proceed, one thing that we do need to adjust is that output value. Right now, we can see that it's just a y. We need to put a y hat in there, and the reason for that is usually y stands for the actual value, and that's what we're going to be using. So, y is going to be the actual value, which we see in reality. Output value is the predicted value by the algorithm, by the neural network. We hat is the output value, basically. That's the denomination for the output value. And the perceptron was first invented in 1957 by Frank Rosenblatt. And his whole idea was to create something that can actually learn and adjust itself. And this is what we're going to be looking at now. So we've got our perceptron. Let's see how a perceptron learns. So, let's say we have some input values that have been supplied to the perceptron and basically to our neural network. Then the excavation functions apply. We have an output. And now we're going to plot the output on a chart. So there it is, our output yi hat. Now, what we need to do is in order to be able to learn, we need to compare the output value to the actual value that we want the neural network to get, right? And that is the value y. And so if we plot it here, you'll see that there's a bit of a difference. Now, we're going to calculate a function called the cost function. It's calculated as 1/2 of the square difference between the actual value and the output value. Now, there are many ways you can come up for cost function. There are many different cost functions that you can use. This is probably the most commonly used cost function, and why it is specifically this function you will find out further down when we are talking about gradient descent. But for now, we're just going to agree that this is the cost function. And basically, what the cost function is telling us is what is the error that you have in your prediction. And our goal is to minimize the cost function. Because the lower the cost function, the closer the I hat is to yi. Okay, so as long as we agree on that, let's proceed. So basically, from here, what happens is there is our cost function. And from here, what happens is now we're going to, once we've compared, now we're going to feed this information back into the neural network. So there we go. There's the information going back into the neural network, and it goes to the weights, and the weights get updated. Basically, the only thing that we have control of in this very simple neural network are the weights. 1, W2, all the way to WM. And our goal is to minimize the cost function. So all we can do is update the weight. So we update the weights, tweak them a little bit, and how exactly we'll find out further down. But for now, we agree that we update the weights, and then we continue. But here I've put up this screenshot of the data just to make one point very clear. That right now, throughout this whole experiment, everything we're doing right now, we're dealing with just the one row. So we have a denizen of one row where we have, for instance, we're dealing with how long you study. And the variable that we're predicting is what results you're going to get on an exam. And the independent variables that we have is how many hours did you study for? How many hours did you sleep? And what did you get on the quiz in the mid-semester? So in the middle of the semester, there's a quiz. What percentage did you get there? Based on those variables, we're trying to predict what score you'll get for the exam. And in an exam, the 93%, that's the actual value. So that's why. So we feed these three values into our neural network again for the second time now, and then we're going to be comparing the result to y. So let's see how this works. We feed these values into the neural network, everything gets adjusted, and weights get adjusted. So as you can see, this is again, we're going to feed the values again. The point here is that we're feeding in the same values. So we only have one row. We're training on one row. This is because this is just a very simple basic example. Then we'll see what happens when there's more rows. So again, we feed these rows in. Our cost functions get adjusted. As you can see, everything happens along those lines. As you can see, every time our y hat is changing, because we've tweaked the weights, our y hat is changing, our cost function is changing. Let's have a look again. We feed those in. E hat is changing, cost function is changing, we get information back, feedback to the weights, so that the weights get adjusted again. We feed in the same values every time, everything gets adjusted, goes back to the weights. And one more time. Feed in, okay? And another time, so we've adjusted the weights, we feed in information, and there we go. And now this time, the y hat is equal to y, cost function is 0. Usually you won't get cost function equal to 0, but this is a very simple example. So hopefully, all that made sense. Every time we feed in exactly that same row, because just in this case, we're just dealing with that one row into our neural network, where then the values get multiplied by the weights, the activation function is applied, we get E hat is compared to Y, then we see how the cost function is changed. Feed that information back to the neural network and adjust the weights again. And then we repeat the same process again with the same exact row. We're trying to minimize that cost function. So up until now, we've been dealing with just that one row. Let's see what happens when you have multiple rows. So here's the full data set. We have 8 rows of how many hours you slept. Or maybe these are different students taking the same exam, how many hours they studied, how many hours they slept before the exam, what did they get on the quiz, and their final result on the test. And as you can see here on the left, I've got 8 of these perceptrons. Actually, they are all the same perceptron. So this is also important to say, I just multiplied it or duplicated 8 times, just so that we can conceptually understand. But the important thing here, it's the same neural network. We're going to be feeding these into the one same neural network, so let's go. Let's get started. One epoch, as you'll hear Hadelin mentioning, one epoch is when we go through a whole data set, and we train our neural network on all of these rows. So let's go. Let's get started. There's our first row, and there's I hat for the first row. There's a second row, there's I hat for the second row. So again, it's being fed into the same neural network every time. I just copied them several times so we can visually see how this is happening. Then again, it's happening again. That's third row, fourth row. There's our Y hat for the fourth row, and so on, basically. then we get the same values for the remaining 4 rows as well. Every time we just feed in a row into our neural network, we get a value. Then we compare to the actual value. So there are the actual values. So for every single row, we have an actual value. And now, based on all of these differences between I hat and y, we can calculate the cost function, which is the sum of all of those squared differences between I hat and y and all that is halved. And there's a cost function. And basically now what we do after we have the full cost function, we go back and we update the weights. We update W1, W2, W3. And the important thing to remember here is that all of these perceptrons or all of these neural networks is actually one neural network. So there's not 8 of them. There's just one. And when we update the weights, we're going to update the weights in that one neural network. So basically, the weights are going to be the same for all of the rows. It's not the case that every row has its own weights. No, all the rows share the weights. And so that's why we looked at the cost function, which is the sum of the squared differences, and then we updated the weights. And now from here, that was just one iteration. Next, we're going to run this whole thing again. We're going to feed every single row into the neural network, find out our cost function, and do this whole process again. Just as we showed previously, where we had just one row and we were doing everything again and again, same thing here, but now we're going to be doing it for 8 rows or 800 rows or 8,000 rows. How many rows you have in your data set, you do this process, and then you calculate the cost function. And the goal here is to minimize the cost function and to get, as soon as you found the minimum of the cost function, that is your final neural network. That means your weights have been adjusted and you have found the optimal weights for this data set that you're training on, and you're ready to proceed to the testing phase or to the application phase. And this whole process is called backpropagation. So some additional reading that you might want to do for the cost function, and I know we just talked about one, and there are many different ones. A good article is located on Cross-Validated. It's called A List of Cost Functions Used in Neural Networks Alongside Applications. So the URL is there, but you can just Google for that exact search term or search phrase, and this one will be the first one that pops up. It's actually got some good examples in application or use cases for different cost functions. So if you're interested to learn more about cost functions, check out this article, and on that note, I hope you enjoyed today's tutorial. I look forward to seeing you next time. Until then, enjoy deep learning.